Hey everybody, it's time for Unit 8, Day 2. We get to look at simplifying our lives a little bit by looking at center of gravity. So let's take a look at the notes for Day 2. Technically, it's called center of mass. Center of mass is a really helpful idea because, like I said, it really simplifies the motion of an object. So a good example is human bodies, right? Human bodies are a really complex system, and technically gravity is going to pull on all your particles. So all your atoms, all your molecules, bones, ligaments, skin, fat, it's all getting pulled by gravity. And if we had to calculate that force and how it would move an object, that would be really complicated. So because talking about the connection to torque last time, each particle is going to have its own torque measurement, which is just really confusing and hard to understand. So what we want to do instead is we want to take an entire object, and for that complex object, just figure out where its center of gravity is. Okay, and that center of gravity is what will help us measure the angular velocity, the torque on the system. It's as if the entirety of the weight of an object is at a single point, okay? That single point is very important because that's how we track its motion, okay? Is that singular point is acting as if the whole object is that singular point. So here we have this gymnast who's swinging on the bar. Her entire center of gravity is here in the middle, like you would expect, and that's the part that's going to apply the weight's gravitational force that's going to supply the torque to make her swing forward. All right, so let's look at that in terms of a flagpole. So you're trying to lift a flagpole. Let's say you just painted it or whatever, and you want to try to bring the flagpole up to vertical. How would you calculate the amount of energy, the amount of force, you'd have to apply to get that to move? You can see the flagpole weighs 3.2 kilograms. It is 1.6 meters long. So its radius is 1.6 meters. And its theta currently is 25 degrees off of horizontal. All right, so is that radius center of gravity? Yeah, okay, so that radius is already measured for the center of gravity. The flagpole is not much taller, but it is taller than that. The center of gravity, by the way, is labeled using that little point there. So, okay, so we have that problem here. So if we want to measure the torque, if you remember from before, torque is equal to the length of your lever multiplied by the force. For us, though, that is going to be the weight. Okay, the force that's being applied is the weight of the that weird reflection going on there. Is the weight is the weight of the flagpole itself. Okay. That still didn't help. There we go. That looks better. Okay, so what we need to do is measure how far out it's actually being pulled and what the weight is actually going to be, times gravity, because the flagpole itself, is 3.2 kilograms, but that's its mass, not its weight. Okay, so let's rewrite that. Now the radius is supposed to be supposed to be a straight push. The problem is though that this flagpole, the weight is actually going to pull straight down, so that angle doesn't really work. What we need instead is our moment arm. We need to measure the radius of the moment arm, which would be R perpendicular, and mg is your weight. Okay, so if you remember from before, the the um, the arm here was supposed to be 1.6 meters long. That's supposed to be your arm. But for finding our torque, lever arm is actually your radius times the cosine of theta. R cosine theta mg. All right, so let's calculate this whole thing. So our radius is 1.6 meters, cosine of 25 degrees, multiplied by our mass, which is 3.2 kilograms, times gravity, which is 9.8. Okay, so let's see how much torque is actually being applied there. 1.6 cosine 25 times 3.2 times 9.81 means that we're at 45 newton meters. So the amount of torque that you'd have to apply to that flagpole to get it to stand straight up would be 45 newton meters. All right, let's go back to the notes. All right, so gravity is what makes this kind of a confusing point, because gravity is always going to pull straight down. It doesn't really matter, what the center of mass and how it aligns with the object. But the idea is that gravitational torque applies to the center of mass, the center of gravity, and it tries to pull it down to equilibrium. So it's still kind of tied into the idea of simple harmonic motion. That's why simple harmonic motion works, because if you have a pivot and you have a gravitational pull, it's going to try to get it to rest at that center of gravity alignment. So the center of gravity is aligned with the gravitational pull. This flagpole would be totally stable straight up and down, because there wouldn't be any torque applied to it, being pulled left or right? Like if it's straight up and down, the flagpole is going to have its gravitational pull be directly aligned with the center of gravity, which is why it would stay in that position. So there's no torque in that position. Also, if it was laying on the ground, it would also be aligned with the pivot, technically, because the pivot is the whole bottom edge of the flagpole. All right, so let's look at some different objects here. So this object is an L bracket, basically, and we're trying to figure out where its center of gravity would be. So on the object, you can see you have two that are on the piece D and B. D and B being on that piece if you're looking at it, it's a uniform thickness. So it wouldn't make sense that either of those would be a good option. If you think about the whole mass as an object, there's a lot of material hanging out on both ends. So the center of gravity should be somewhere in between the two ends. C is way too far out. So the only reasonable option would be A. So for an L-shaped material, the center of gravity is actually outside of the material itself. It's not even inside of the piece. The position of balance, or the center of gravity, is where your torque is 0. Okay, so, and knowing that, we can write an expression, but I want to quickly show you how that works with a ruler. So that we have a meter stick here, right? And if I balance the meter stick on my fingers and I pull my fingers together, what you'll notice is if I move them slowly, the one finger will kind of stop and then the other one will slide until the weight gets heavier on that one finger, and then the other one will slip and move, and then it will get stuck, and then the other one will slide. And that's got to do with static friction and kinetic friction. But eventually, if you keep moving nice and slow and try to keep it even, because of the forces going on there, the torque of the center of mass. Gotta start again. Do the last little bit. Okay. Yep. Right in here, if I can roll one finger over a little bit. There's your center right there, and it's perfectly balanced. So the weight of it is pulling straight down onto my finger. The weight of the whole meter stick is pulling straight down on my finger, and it's balanced. The force is 0 right at that center point. So there's no torque force. Well, the torque forces are balanced, so the overall torque force is 0 for that point. Okay, so that's a good visualization of how that works. All right, so let's think about gravity and a pivot to figure out how that equation would work. So let's say we have dumbbells, and the dumbbells are balanced, much like the meter stick was balanced on my finger. It must be at the center of gravity. The pivots have to be located at the center of gravity. The torque on either side, therefore, is balanced, as I mentioned, on a balanced system like that. So you can have two masses with different weights. If it's balanced, if it's not falling in either direction, then we know that the torque overall is going to be 0. The center of gravity is a balance point for that. So knowing that the torque on both sides is equal and opposite to each other, we can say that torque 1 and torque 2 are equal to each other. Using our equation that we used before, knowing that R is your radius and W is your weight energy, we can see that for torque 1, it's the center of gravity, which is your center point, minus your x1, which is the position of that weight, times mass 1 times gravity is going to be equal to the R2 position and the weight 2. So the overall equation on that system is going to be torque 1 and torque 2, which we know now is center of gravity minus x times the mass 1 times gravity, subtract, because it's on the other side of the fulcrum, one has to be positive and one has to be negative. of mass 2 times its location and gravity. And if you solve that for the center of gravity, because we want to find the center of gravity, then it's a ratio of the masses. Okay, so the overall idea is that if you know your position of the masses and you know their masses, it's a ratio of the torque applied and the weight. So it's torque over weight, basically, to find the center of gravity. Okay, which should make sense that it's, torque and the relationship to weight, a ratio of torque and weight is the idea. So that's how you find the center of gravity. If you knew all the variables, you have to know positions, you have to know masses, but that's how you would find it. Because the center of gravity depends on not just the mass itself, but how far the mass is from the center. And the center of gravity tends to lie closer to the heavier objects, of course, in a balanced system. So it's not just where the objects are, but how heavy they are. All right, so let's look at a problem with a weird dumbbell. They wouldn't really have, dumbbell that's set up like this. That would not make sense, but you have a dumbbell that has 2 different masses on either end. One mass being 10 kilograms, the other mass being 5 kilograms. Talk about a really dumb dumbbell, right? And you want to know, you don't want to look like a putz in the weight room, right? You want to be able to pick this up and have the balance perfectly, figured out. So the overall length of this is 1 meter. That's that's not even a dumbbell, that's huge. It's like a regular weight bar. CG stands for center of gravity. All right, let's look at this together. So we have our dumbbell here, 10 kilograms on one side, 5 kilograms on the other. That's just an approximation of where your center of gravity is. And what we want to do is, using the equation that we just saw, is calculate your center of gravity. So the center of gravity for an object is related to the torque applied by each part, x1, mass 1, plus x2, mass 2, over the ratio of your masses. So mass 1 plus mass 2. Okay, so for this system, you can see that position 1, x1 is 0, and that's your 10 kilogram, which that's gonna be 0 now, plus x2, which is 1 meter, and 5 kilograms. So that's going to be 5. So 0 plus 5, the numerator is going to be 5. And then on the bottom, we have 10 kilograms plus 5 kilograms. So that's 15. So it's 5 over 15. The units are weird though, because on top it's actually kilogram meters or meters kilogram, but kilogram is going to cancel out because the numerator is just kilograms. So 5 divided by 15 gives us, that's a third, right? So 0.33 meters. 0.33 meters is this right here. That's your center of gravity, is at 0.33. So just a quick example of how to find your center of gravity. Oh, that's it. All right. So hopefully that was helpful. We have a lab coming next class that you'll be doing at home. So I'll be sending you some information about that. And and we'll move on from there. I'll catch up with you guys later.